For this video, we're going to take what we learned about pH and extend it a little bit further. So we're going to start here with percent dissociation or percent ionization. This is going to describe the strength of an acid just like the Ka would, or this is going to describe the strength of a base just like the Kb would. We know that the greater the percent dissociation or the greater ionization, the stronger the acid or base will be. If you remember here, strong acids or strong bases are 100% dissociated or 100% ionized. They form ions 100%. So basically, the greater your percent ionization, the stronger the acid or base will be. So the equation to figure this out is actually pretty simple. For the percent dissociation or percent ionization, just take the concentration of the H plus, all right, put it over the concentration of the acid times 100. Or if this is for a base, you take the concentration of OH minus over the concentration of the base times 100. All right. And the higher the number here, the closer you are to 100, the stronger the acid is going to be. Remember, strong acids or bases are 100% dissociated here. So let's look at this pretty easy example here to start. This says, what is the percent dissociation for 0.10 molar HCOOH, which contains a concentration of H plus being equal to 4.2 times 10 to the minus third molar. All right, so this is an acid. So to determine the percent dissociation, we're going to take the concentration here of the H plus over the concentration of our acid and times 100. So they gave us the concentration of H plus to be 4.2 times 10 to the minus third molar. And this is going to be over the concentration of the acid, which is 0.10 molar, times 100. When you do your math here, it comes out to be about 4.2% ionized. So in the grand scheme of things, this is a weak acid. Obviously, if this was a strong acid, it would be 100%. The value here would be 100%. So obviously, this is not 100%. So this is going to be a weak acid. It's only about 4.2% ionized, or it only has a percent dissociation of 4.2%. All right, so you can do this for an acid or a base. It's called percent dissociation or percent ionization. Essentially, it's telling you how strong the acid or the base is. Let's look at another example here. This one says calculate the percent ionization of 0.15 molar acetic acid, and they gave us the Ka here. All right. In order to do percent ionization, we need the concentration of the H plus over the concentration here of the acid itself. In the problem, they gave us the concentration of the acid, but I don't have the concentration of H plus. So I'm going to have to find that here. All right. This is a weak acid. So if you want to find the concentration of H plus for a weak acid, you're going to have to do an equilibrium problem. You're going to have to do an ice table here. All right. So this is acetic acid. So acetic acid is going to be in equilibrium here with its ions. So acetic acid is going to be HC2H3O2, and it will be in equilibrium with H plus C2H3O2 minus here. We're going to set up our ice table. So initially here, we know the concentration of the acetic is 0.15 molar. There's going to be none of the products present. We don't know any of the concentrations at equilibrium, so we're going to do this change in terms of X. The reactants are being used up. So it's minus X, products are forming, so they're plus X. Now we can write our equilibrium concentrations in terms of X, 0.15 minus X molar for the acetic, X molar for each of your products here. We can write the Ka expression here for this equilibrium. Ka is going to be equal to concentration of your products, concentration of H plus, times the concentration of the C2H3O2 minus, all over the reactant, the acetic acid here. So now that we have our Ka expression here, our equilibrium constant expression, we can plug in. We know Ka is 1.8 times 10 to the minus fifth, and that's going to be equal to x squared all over 0.15 minus x here. We can do the x approximation because this is a weak acid. So when we solve this, the math is a little bit easier here. So x will come out to be 0.0016 molar. And remember here, according to how we have this set up, that's the concentration of H plus here in the ice table. So now I know the concentration of H plus. I can find the percent ionization here. We're not asked to find the pH. We just want to do percent ionization. So we need to take the concentration of H plus all over the concentration of the acid and then times 100 here. So when we plug in, we have 0.0016 all over our 0.15 times 100. When you do the math, it comes out to be about 1.07%. All right, so in the grand scheme of things, this is a pretty weak acid here. So just pay attention to what you're solving for. X in this case was the concentration of H plus. All right, so that means I'm doing the percent ionization here for an acid, so I need the concentration of H plus over the concentration of the acid times 100. We have another example here. This one says lactic acid, and we're given the formula for that, is a waste product that accumulates in muscle tissue during exertion. In a 0.10 molar solution, lactic acid is 3.7% dissociated. So right there, because of that percent dissociation, I know, obviously, it's not a strong acid because it's not 100% dissociated. We want to calculate the value of Ka for this acid here. All right, so in this problem, we're given the percent dissociation and the original concentration, but we're not given anything with regards to calculating the Ka here. We're going to have to use this percent dissociation to figure out our concentration of H plus essentially. We already know here that the concentration of H plus over the concentration of the acid times 100 is equal to the percent dissociation, which in this case we know is 3.7%. So if we plug in what we know, the concentration of H plus, we don't know, all over the concentration of the acid, which is 0.10 molar. When we times 100 would be equal to 3.7%. So let's divide the 100 by both sides. So this is going to be equal to 0.037. So now you just need to do your math here, cross multiply, solve for the concentration of H plus. We get that concentration of H plus to be equal to 0.0037 molar. All right, so now we know the concentration of H plus here. Realize if you were doing an ice table, the concentration of H plus would also be equal to the concentration here of the other ion here. So this would also be equal to the concentration of the C3H5O3 minus. All right, so now you know each of their concentrations, and we already know the original concentration here. If we were doing this, we would do the X approximation, so we don't have to worry about getting rid of X on the bottom. So we can write our Ka here, essentially, skip the ice table. We have Ka equal to, if we were writing this out, we can write the reaction here so we can see it at least. We have HC3H5O3 would be in equilibrium with its ions, H plus the C3H5O3 minus here. So if we're writing the Ka for this, we'd have the concentration of H plus times the concentration of the C3H5O3 minus all over the concentration of the HC3H5O3. So we're trying to solve for Ka here. So when we plug in our values, remember the concentration of the H plus and the concentration of the C3H5O3 minus are going to be exactly the same here, which we already calculated, 0.0037. So that'll be squared all over your concentration here of your lactic acid. Remember, if you were doing the equilibrium table, you would have 0.10 minus X. The X we would make negligible. So the bottom is just going to be 0.10. 0 here. All right, so when you do your math and you plug and chug with sig figs, you should get 1.4 times 10 to the minus fourth here for the Ka of the lactic acid. So this is just another example using that idea of percent dissociation or percent ionization to be able to get the concentration of H plus and then taking that further to find the Ka. Another idea that we want to look at here is something called polyprotic acids. Poly meaning many. Essentially, these are acids that can donate more than one H plus. So monoprotic acids are acids that only have one H plus to donate here. And typically that's what we've been looking at so far, like HCl or HNO3. They only have one H plus that they can donate. A diprotic acid would be an acid that can donate two H plus. So di meaning two. So H2SO4, sulfuric acid, has two hydrogens that could be donated. And then obviously you could have like a triprotic acid, something like phosphoric acid, H3PO4, would have three H pluses to donate. So those are polyprotic acids. Polyprotic bases basically can accept more than one H plus. For example, PO4 3 minus. It could accept three H pluses. So that would be a polyprotic base. These polyprotic acids dissociate in steps, one proton at a time. Okay, so basically it would lose one proton at a time here, and each step would have its own Ka value. All right, so that's important. Anytime you have a polyprotic acid here, it's going to dissociate in steps, and every step will have its own Ka value. If we look at phosphoric acid here, dissociating kind of one at a time, we know that it has three hydrogens here available to give up. So this is a triprotic acid. Notice in this reaction, it's reacting with H2O to form the hydronium ion, H3O plus. That's basically the same thing as losing an H plus here. All right, so for the first hydrogen that H3PO4 loses, you get H2PO4 minus forming plus that hydronium ion. So you can write a Ka for this, products over reactants, and it has a Ka value. The important thing to note here is this first dissociation, which we call Ka1, is always going to be the greatest. All right, the Ka1 is always going to be the greatest, and the ones that follow are going to be much smaller Ka values. Essentially, the acid is getting weaker with each H plus that's removed. All right, but it's harder to remove each H plus after this. Okay, so you're always going to have the greatest Ka being Ka1, and then it's going to get smaller every time you remove another hydrogen. So now if you take this H2PO4 minus that formed, remove a hydrogen from it, all right, forming HPO4 2 minus and another hydronium ion here, basically the same as H plus. You can write your Ka for this step, and you see the Ka is definitely smaller than Ka1. And now we can remove the last hydrogen here, the HPO4 2 minus can react with water, giving you PO4 3 minus plus the hydronium ion. You can write the Ka for that step, and you can see again that the Ka3 here is even lower than all the rest. So the first dissociation is always going to have the greatest Ka, and only the first dissociation here is actually important in determining the pH here for the polyprotic acids. Obviously, if this Ka is the greatest, this is the one we need to worry about the most when we're determining pH. So you don't have to worry about the Ka2 and the Ka3 in this instance. If you were doing a problem with this, you can just focus on that very first dissociation because that one is the greatest. Let's look at an example here. For this one, it says if the concentration of H2CO3 is 0.0037 molar, what is the pH and concentration of CO3 2 minus? All right, so it's kind of two separate problems here, and they're giving us Ka1 and Ka2 because this is a diprotic acid. So the first thing we're going to do is we're going to write the first dissociation here. Essentially, we have this carbonic acid here. It's going to lose its first hydrogen, forming H plus and HCO3 minus. All right. The first dissociation, the one involving Ka1, is going to be the one that you're going to use to determine the pH here, because this is going to be the greatest of the Kas. It's going to be the one you need to use to determine the pH. So we have our first dissociation written. Remember, it's in equilibrium. This is a weak acid here. So we set up our ice table. Now we're going to go and plug in what we know here. Initially here, we know the concentration of the carbonic acid from the problem. We know that both of the products here, both of the ions that it dissociates into are 0. There are no products present initially. So now we need to think about the change here in terms of X. We don't know any of the concentrations at equilibrium. So the reactants are going to be used up, negative, and the products are going to be formed. So they're going to be positive. Because of the 1-to-1 ratio, we have negative X for the reactant here. It's being used up. And both of the products here, both of the ions are positive X. So now we can take our initial and our change here to plug in our equilibrium values here in terms of X. So I write the equilibrium values for each of these substances. Realize here again, this is a weak acid, so we can do the X approximation, get rid of the X here essentially in our math. I didn't show all the math. I just crossed it out there in the table. Realize when you do solve for X and you go back to plug in, you would need to plug it in. I was just showing you here that this is an X approximation problem again. When you plug into your Ka and solve, you do get X to be, obviously the concentration of H plus, to be 4.0 times 10 to the minus fifth molar. When you do the negative log of the concentration of H plus, you get the pH being 4.40. All right, even though there's two Kas here, the pH is determined by the very first Ka because it's the greatest when you have these polyprotic acids here. So again, I did kind of skip out on some of the work, but you pretty much already know how to go about solving this problem. I just wanted you to see how to go about getting this answer just using the very first Ka. So now we need to go and actually focus on the second part of the problem. We still need to determine the concentration of CO3 2 minus. Well, in that first dissociation, we did not get to the CO3 2 minus yet. We only stopped at HCO3 minus. So now we need to do the second dissociation. We need to lose the second hydrogen in order to form that CO3 2 minus. So I write my second equilibrium equation. The HCO3 minus was formed from the first dissociation when the first hydrogen was lost. So now this guy is going to lose a hydrogen and it's going to form H plus and CO3 2 minus here. It's dissociating in to these two substances. So we want to know the concentration of the CO3 2 minus. So now we're ready to fill in our ice table here. This is a weak acid, so you need to do the ice table here. But there's one slight little difference, okay? We know the initial concentration here of the HCO3 minus because we just figured that out from the previous step, from the previous ice table. But that's also the initial concentration of your H plus as well. Remember, in the previous problem, we figured out the concentration here of your H plus. So the only real difference here is now you need to note that you have a starting value here for the concentration of H plus because you just figured that out in the previous step. So that's something to maybe make a note of, maybe star and circle, that if you keep going into the next, after Ka1, head into the second dissociation, you will have a starting value there for your H plus. And then the CO3 2 minus is still 0 initially. There's none of that. So now we need to think about our change here. Obviously, we don't have any of the CO3 2 minus, so we're missing one of the products here. So we know the reaction is going to go to the products. So we're going to be minus X for the reactant, plus X for both products. Now we can do our equilibrium concentrations. We can plug in our equilibrium concentrations here and realize that we can get rid of the minus X and the plus X when we do our math here. I'm crossing it out right in the table just to show you that when you did the math, you could cross out both of them. They're going to be negligible because this is a really weak acid now, so they can be totally ignored and we don't have to worry about them for the math. When you plug into your equilibrium constant expression, all right, you would have to write it all out. Again, I'm kind of skipping steps here to save time. When you plug it in and you solve for X, X will be the concentration here of the CO3 2 minus, and you get 5.6 times 10 to the negative 11th. Notice the concentration here of the CO3 2 minus is equal to the Ka2 value. So anytime you're doing one of these problems and you get all the hydrogens removed and you have just the conjugate itself remaining, that Ka value is going to be equal to the concentration of the conjugate. So like if this was a triprotic acid, if you remove all three of the hydrogens, the concentration of that conjugate would be equal to the Ka3 because it would take three dissociations here to get all the way to the concentration of the conjugate. So you might have to show work for this, but in case you're doing a problem here where that doesn't require work, look at how much time you could save. You immediately knew the concentration here of this conjugate when you remove both of the H pluses and you get it down to CO3 2 minus is going to be equal to the value of the Ka at that step. All right, so in this case, it was equal to the value of the Ka2. So that's just something to be aware of in case you see this maybe in a multiple choice or something and you can save yourself time, but obviously you know how to do the math as well. Now we're going to look at common ion again real quick. Remember, common ion is a reduction in solubility. Something becomes less soluble when you add a soluble compound here containing one of the same ions. It's added here. We reduce the solubility of our original compound. So this will affect pH. Basically, a weak acid or base will dissociate or ionize less than if it were alone. So anytime you have a common ion here, you need to understand that common ion means there's going to be a reduction in solubility. So if we want to determine the pH here of 0.30 moles of acetic acid, Ka is given, and 0.30 moles of sodium acetate in 1 liter of water. The first thing you need to recognize here is that this C2H3O2 minus here in the sodium acetate is a common ion. We're trying to find the pH. This is the weak acid. This is a salt. All right. You need to realize we don't care about the sodium. It's the C2H3O2 minus that's in common here with the weak acid itself. So now we need to consider that in our problem. So the acetic acid is a weak acid, so it's going to be in equilibrium with its ions. We can write the dissociation equation here. Remember, it's in equilibrium. And now we can fill out our ice table. We have the initial concentration here of the acetic. Remember, it's in moles, but they told you the number of liters, and it's just 1 liter, so that makes it really easy. It's just 0.30 molar. You can't be in moles here in your ice tables. You got to either be in concentration or pressure. There's no H plus initially, but because of the common ion, there is going to be a starting amount here of the C2H3O2 minus. All right. Remember, we don't care about the Na, but right here, all right, according to this, there's going to be 0.30 molar. All right. When you do the moles over the liters, there's actually a starting value here for the acetate ion. All right, so that's kind of the only difference here. You have a starting value in your ice table for your common ion. Now you're just going to approach the problem the same. You need to think about your change here in terms of x. So we have a 0 as a starting value or an initial value for one of the products. So we know we're going to form the products here at equilibrium. So the reactants are going to be lost, negative x. Both products are plus x. Again, this is all 1-to-1. That's why we only have x's here. Now we can fill in our equilibrium in the data table. And again, this is going to be another x approximation. We can get rid of the minus x and the plus x here to make the math a little bit easier. You still have to set up your Ka. You still need to plug in and solve for x. I'm just saving some steps here because we've seen this. I just want to kind of walk you through it a little bit quicker here. When you do solve for x, that's going to be equal to the concentration of H plus, and we get that being 1.8 times 10 to the minus 5th molar. Now that we have the concentration of H plus, pH is equal to the negative log of the concentration of H plus. So when you do the math, it does come out to be 4.74 here. All right. So just be aware that anytime you have a common ion here involved when you're doing the pH problem, it will affect the overall pH. All right. So remember, common ion, the big difference is you have a starting value here. You have an initial value for one of your products. Usually in a lot of these problems, the starting value here for both of your products is 0. But when you're doing a common ion here with these pH problems, one of your starting values is not going to be 0 because of the common ion. And then you just approach the problem the way you normally would. We already know about the acid dissociation constant Ka and the base dissociation constant Kb, and we talked about the dissociation constant for water Kw being equal to 1 times 10 to the minus 14. If you take Ka times Kb, that will equal Kw. So Ka times Kb equals 1 times 10 to the minus 14. This is given on your equation sheet, and sometimes this is important here. If you have a Kb in a problem and you need to find a Ka, you can use this idea. All right, Ka times Kb equals 1 times 10 to the minus 14. So if you know a Ka, you could quickly find a Kb. Or if you know a Kb, you could quickly find a Ka using this relationship here. Now, you can also have a pKa here and a pKb. Essentially, a pKa and a pKb are telling you how acidic or basic a hydrogen or hydroxide is in a molecule. It's very similar to a pH or a pOH, but in this case, it's in terms of a pKa and a pKb. It's very similar here, though, in terms of the equations as well. A pKa is equal to the negative log of Ka, just like a pH is equal to the negative log of the concentration of H plus. Okay, so a pKb is going to be equal to the negative log of Kb. All right, and when you take pKa and pKb and add them together, you get 14. Just like if you took pH and pOH and added them together, you get 14 as well. So essentially, these pKa's and pKb's are just telling you how acidic or basic a hydrogen or hydroxide is here. These little equations are important. They are on your equation sheet, but sometimes you need to use these in problems here, or we might talk about these pKa's and pKb's when we get to titrations and buffers. But the key is you definitely need to be aware of these and know how to use them in problems. A little bit more about this Ka and Kb relationship here. If you have strong acids or strong bases, obviously we know you're going to have a larger Ka or a larger Kb. All right. Remember here, products over reactants for a K. So if you have a strong acid or strong base, they're 100% associated. You have more of the products, so you're going to have a much larger Ka or Kb. But your pKa or pKb are going to be lower. Essentially, think about this in terms of pH. A lower pH means it's going to be stronger. So that's the same idea here. If you have a lower pKa or a lower pKb, you're going to have a stronger acid or base. And then for weak acids or bases, obviously you have smaller Ka or Kb values because products over reactants. For weaker acids and base, you have more reactants, so a lower Ka or Kb. But then your pKa or pKb are going to be higher for weak acids. So I just want to make sure you understand this relationship. Be careful here. They're kind of opposite. If you have a higher Ka or higher Kb, you have a stronger acid or base, but then it's a lower pK or pKb here for them to be stronger. So just be aware of this relationship and don't fall for any traps. Understand they're kind of opposite. Let's look at an example here. We want to calculate the pH of 0.20 molar lactic acid. They gave us the formula there for lactic acid with a pKa of 3.08. All right. Obviously, lactic acid is not one of the strong acids, so it's going to be weak. So we're going to need to do an equilibrium here. We're going to need to have an ice table. So I'm going to write my equilibrium here. I have the C3H5O3 in equilibrium with its ions H plus and C3H5O3 minus. All right, so that's the equilibrium we're looking at here. The weak acid dissociating into its ions. Remember, this is not going to be 100% because it's weak. So when we set up our ice table, initially here we know the concentration of the lactic acid is 0.20 molar. There's going to be none of the products here, so we know that we're going to form the products. So we're going to have negative X for the change for the reactants, positive X for the change here of both of the products. When we fill in our equilibrium values, you have 0.20 minus X molar and X molar for both of the products here. All right, now we need to write our Ka expression and plug in. But before we do that, you need to notice here in this problem, we were given a pKa. We don't have the value of Ka, so we're going to need to find that first. We know pKa is equal to the negative log of Ka. So if we have the pKa here, we can get the Ka, all right, by doing 10 to the power of the negative pKa. Think about how we would do this if we knew here the pH and we wanted to find the value of the concentration of H plus. We would do 10 to the power of the negative pH. So in this case, to get the Ka, we do 10 to the power of the negative pKa. So when we do that, we get 10 to the power here of negative 3.08, and that's going to be equal here to 8.3 times 10 to the minus 4th. So now we have our Ka value. Now we can write our Ka. Ka is going to be equal to products over reactants. So we have H plus, concentration of H plus, times C3H5O3 minus, all over the concentration of your reactants here, your HC3H5O3. We already know the Ka because we just found it. All right, we found it to be 8.3 times 10 to the minus 4th, and that's going to be equal to x squared all over the 0.20 minus x, which again, we can do the x approximation here because this is a weak acid. All right, so that makes your math a little bit easier. Just solve for x. So when we do that, we get 0.013 molar. Remember, this is the concentration here of the H plus. So if we want to find the pH, pH is going to be equal to the negative log of the concentration of H plus. So that's going to be the negative log here of 0.013. When you do the math, pay attention to your sig figs. It comes out to be 1.89. And that's your final answer here for that pH. So again, it's pretty much a basic equilibrium problem for a weak acid. The only difference was they had given you a pKa and you had to find the Ka in order to solve the problem. So make sure you understand these relationships here involving Ka, Kb, and pKa, pKb. Let's look at one more example here. This says, what is the pH of a 0.045 molar solution of KOBr? They gave me the pKa of HOBr being 8.63. And there's a little hint here because you don't know entirely everything that's going on here. There's more coming, but in order to do this problem, you might need this little hint. It says, write the weak base reaction of OBr minus with water first. All right, so that's what I'm going to do. I'm going to write this weak base equilibrium reaction with water. So I have this OBr minus reacting with water here. It's going to be in equilibrium. So what's going to happen here is it's telling me it's a weak base. So I know I need to form OH minus here. It's going to pick up an H, and we're going to get HOBr as one product plus OH minus here. All right, we knew that OH minus had to form because this says that this is going to be a weak base reaction here. So now I can set up my ice table for this. Water is a liquid, so it doesn't participate in your ice table here. My initial concentration of the OBr minus. Realize here they gave me the concentration of KOBr. Well, if this was dissociating, because it's a salt, it would dissociate here. For every one of the KOBr, you'd have one OBr minus. So if you know the concentration of the KOBr, it's going to be the exact same concentration of the OBr minus. So this concentration is 0.045 molar. I don't have any of my products here, so now I need to think about the change in terms of X. The reactant's going to be used up, so it's minus X. Products are forming, so they're positive X here. At equilibrium, I have 0.045 minus X molar, and both of the products are going to be X molar here. All right, so now I'm going to write my Kb for this. Remember here, you are forming OH minus. So that's telling you you need to write a Kb here because this is a base. All right, so when I write my Kb expression, I get Kb equals products over reactant. So I have the concentration of HOBr times the concentration of OH minus all over concentration of OBr minus here. All right. Realize though, you just wrote a Kb, and in the problem, we were given a pKa. Well, that doesn't work here. Even if you get this to a Ka, you're going to have to even go further because we need a Kb here. So we already know that pKa is equal to the negative log of Ka. So Ka would be equal to 10 to the power of the negative pKa. So when we do that math here, 10 to the power of negative 8.63, we're going to get 2.0 times 10 to the minus 9. So now we know a Ka here, but that's not good enough. We need to know a Kb. Remember here, we know that Ka times Kb equals Kw, which is equal to 1 times 10 to the minus 14. So if we want to solve for Kb here, Kb is going to be equal to that 1 times 10 to the minus 14 divided here by your Ka. Look at the equation here. If you wanted to solve for Kb, you would have to divide the Ka by both sides. So it's the Kw, which is 1 times 10 to the minus 14, divided here by the Ka, which is 2.0 times 10 to the minus 9. So that gets you your Kb here. All right, and my Kb ends up coming out to be 5.0 times 10 to the minus 6. All right, so you can see how you had to use your knowledge here of pKa and then use your knowledge of Ka times Kb being equal to Kw in order to get the Kb here. This requires you to understand that you formed OH minus, you were writing a Kb, you needed the Kb value. So pay attention. If you're forming OH minus, you need a Kb. If you're forming H plus, you're going to need a Ka here. So now that I know my Kb, I can plug in what I know to my Kb expression. So I have 5.0 times 10 to the minus 6 being equal to x squared all over this 0.045 minus x. We can do the x approximation, makes it a little bit easier to solve for x here. When I do solve for x is going to be equal to 4.7 times 10 to the minus 4th molar. And realize here that x is your concentration of OH minus. This is not equal to the concentration of H plus here. All right, you want to find the pH? Well, you're going to have to get a pOH first. We know that pOH is equal to the negative log of the concentration of OH minus. So we're going to have the negative log here of 4.7 times 10 to the minus 4th, and that's going to give us 3.33. We know this answer would not make sense here as being our pH because this is in the acidic region and we have a base here. So remember here, pH plus pOH is equal to 14. So 14 minus 3.33 is going to give us our pH, which is 10.67. This makes much more sense here because this is in the base region, which is what we're looking at. We're looking at a base here, so we should get a number that's above 7. So this is pretty much just a basic weak equilibrium pH problem, but you had to be careful, make sure you know you need a Kb and how to actually get the Kb from the pKa.